The thing that we want to look at is what the materials are like. In all AC analysis, one of the difficulties is being able to handle the nonlinearity or the saturation of the steel. So if we have a look at some of the materials that we've defined here, the structural parts are made of carbon steel here, and if we look at the properties of this carbon steel, we'll see that it has a magnetic permeability, which is nonlinear. We also have a resistivity or conductivity, and of course there's other material properties that we have assigned to this. Of course, we can also do some thermal analysis, and so we've assigned thermal properties as well. We won't be showing this today, but certainly we can do also thermal analysis for these types of problems. Of course, we also have materials such as copper. Here we have, of course, copper has got a relative permeability of 1, and also the copper varies, the copper resistivity varies with temperature, and we have actually modeled this by entering different parameters here. And so there are several materials. Another property that we'll be interested in is going to be the loss characteristics, and of course the core here could be made of N36 material, and as you can see here, we've entered loss material data and at different frequencies, and we will be using this to actually calculate the losses in the core itself. In effect, we actually fit these curves using the Steinmetz equation shown here, and we'll be using these. We fit these the Steinmetz equation, and we have the different parameters for that particular material. And we will use these materials properties later on after solution to have a look at what the losses are like. Now, some of the other things that we may want to model with these for these transformers is one of the things we'll be showing you is going to be also some circuit capability with our AC solver. So the first thing I want to do is have a look at what happens with these thin materials. And what I've done is I've built a simple 2D model, and I'm going to use this divide and conquer type of scheme to try to illustrate some of the analysis that I would do in this particular application. So what I've done here to start off with is we'll start from our familiar skin depth type of calculation to see how we can handle the nonlinearity of the steel and how it's handled in MagNet. So here I have this is actually a 2D model that we can solve in both 2D and 3D, but in reality it is really a 1D model physically, because what we've done is we've made sure that the top boundary and the bottom boundary here, that the flux will be normal to that. It's a current carrying block of copper, and we will look at the results of this as a function of at a specific frequency. And because this is the field is normal at this boundary, essentially what we've done is we created a set of images that goes from the top of the slab all the way up to infinity, and the same holds through at the bottom here. So this is essentially the equivalent of what we consider the analytic version of the skin depth, where we're actually calculating, we'll be calculating an infinite slab with a field that is going to be parallel to that face. And so let's just solve this here and quickly do a time harmonic solution on that. Now, one of the things that we can get immediately from it is going to be the ohmic loss, and you can see that the losses are quite large in this particular model. Let's get back to the view here, and we'll look at some of the fields here. Let's start off we'll turn off the flux plot here, and we'll just look at the current density. Now, I want to look at the current density because that's going to be an indication of the losses that in this model. So you can now see the current distribution, and you can see it is very constant along the width of the model as expected, and really the only variation is along the x-axis here. So let's have a look at what the field looks like along that x-axis. And we'll use a tool here called field line graph. And so we'll go from about halfway up the side here all the way to the edge. And you can see that you get a sort of an exponential decay along that line. And what I'll do here, what I want to do here is compare this to the traditional skin depth calculation. As you can see here, I'm just going to expand this here. Oops. You can see that I have plotted on the same chart the result from the 2D FEA, the same chart that I generated in MagNet, as well as the theoretical curve. And you can see here that there is no difference between the two, so that model is actually showing you that with a simple model we're now can easily demonstrate the skin depth effect. Of course, we're more interested in viewing what happens in the nonlinear case before we do. So I'm going to bring up now a model which is essentially the same thing, but with a ferromagnetic material. So here's our model. It's the same thing, but now if I look at the materials here, we have what's the nonlinear conductor. And if we look at the properties for that, you can see that it has a nonlinear magnetic permeability and a conductivity of about 11% IACS. And if we solve that, again, we can see the losses calculated here. And if we go back to the view and we'll look at the same field we were looking at before, we'll look at the, and turn off the contour plot here. You can see that the plot is rather different. Let's look at that same contour again. So right down the center. And you can see now that it is still a somewhat exponential, but it has a very different curve than what we had for prior to this with the copper slab. Now, in a nonlinear curve, the nonlinear approximation for the AC analysis is an approximation. Now, the nice thing is about a 2D analysis is we can actually do a full transient analysis with it being taking a very short period of time. So let's solve this problem with the transient solver. So let me open the solution for the transient analysis here, and we'll have a look at what that looks like. So we're using the same materials as the same model, and I've actually solved this, even though it doesn't take very long. I've actually solved this, and we can have a look at some of the results for this. So if we look at now the field at a specific time step here, and we'll choose our time, some arbitrary time here, and we should see a rather different pattern. And this actually can be animated, so let's just generate an animation of that, and we'll see how the field varies as a function of time. So as you can see, we're generating the animation. You can see the propagation of the field into the slab, and so on. So this animation is almost over. Okay. Okay, now there's our animation. I'll slow this down a little bit. So you can see how the energy actually flows from the surface inside, and therefore we can see how the energy flow is. Now, this simulation didn't take very long to run. However, in a larger system like a transformer, like the 3D model of the transformer I showed you previously, this type of calculation is going to take a long time. So what we've done is we've actually created what's a certain boundary condition called the surface impedance boundary condition, which allows us to reduce the model size. Now, I have here a model where I have actually created the surface impedance, and you can see it from the texture on the surface. And if I remove that texture, we'll see that behind it, it looks a lot like what we had before. But this is going to be a 3D problem. Of course, this is going to be a little bit larger model because now we also have to model along the length and not just simply in the plane. And we can solve this with the time harmonic 3D solver. And as you can see, the solution takes very little amount of time, and you also get the losses in the same way as we did before. Just as a comparison here, if we go back to our PowerPoint here, you can see that the losses for the nonlinear AC analysis are actually quite a bit smaller than the losses from the nonlinear transient. And what is important here is the result from the nonlinear AC analysis with the 3D surface impedance boundary condition. And you can see that the difference between those two numbers is actually very small, in comparison. And if you think about a 3D analysis, it could take several hours. And you saw how quickly it actually was solved with our time harmonic 3D solver. You can see that there's going to be a significant time savings with that. So I have also prepared a comparison with different frequencies for our 2D transient and also the 3D surface impedance boundary condition. So let's make that larger so that we can see that. I have got all the points on this curve because the 2D analysis in here, the 2D transient analysis, as the frequency goes up, the solution time becomes very, very long. In fact, when I'm looking at about 100 hertz here in this particular problem, it can actually take a day to day and a half to solve. So I haven't completed all these analyses. I haven't been adding points on this curve. But you can see that the two curves are actually matching quite well. And I have here the actual data that we've calculated. As you can see, that as the frequency goes up, the match gets even better. So you can see that it's down below here at the very low frequency. It's about 10%, but as we go up in frequency, the difference gets smaller and smaller. Now, how do we compare that to, let's say, a more 2D-like analysis? I have here a model which is going to be quite similar, and this is a more of a 2D model, and again, we're using the same material for the conductor. What we're using here is we're using symmetry. We're looking at it sort of like a quarter of the slab here, so it would be somewhere around here. And so if we zoom in here, let's have a look at what that looks like. This is solved 2D, again, as a 2D with time harmonic analysis. So let's have a look at what the what's J field looks like for this. And of course, you can see how it changes. You can see that at the edge here that it's different, but overall, for large portions of the volume, it's quite. It looks a lot like our 1D type of analysis. And of course, we would expect that if we use the surface impedance boundary condition, that even though this area might be give you a difference, that overall we should get a pretty good result with the 2D with the 3D types of simulation. And for that, we can open up the Transient. And we can do the same thing there. We could run the same Transient 2D simulation. But what's important really for that Transient simulation is going to be what we get here in the ohmic loss. So we have our number here, and I'll just bring up very quickly here the results I get for that a comparison between the same comparison we did for 2D and 3D. So we have our 2D nonlinear AC solution, which gives us 83 watts at 400 hertz, and you can see that the one that actually the 3D nonlinear AC with surface impedance boundary condition gives approximately the same thing as a 2D linear AC, and it's quite close to the Transient. And if you look at 1 kilohertz, we're still quite close in terms of losses, less than 7 parts in 130. So it's quite a small difference. One of the things that is also available, if you like the surface impedance, when you use that, you don't actually get the field distribution inside the volume. But we also have had features that we can actually model the inside in a more efficient way, and one of those features is the using mesh layers. If I look at the solution mesh for this problem, you can see that it's quite uniform. I have a lot of elements in this case, and let's have a look at how we can actually use, for example, a series of linear layers, uniform layers. Okay. And zoom in here again. And we'll get the solution mesh. And you can see now that we've got these layers that are generated from the surface. They're a little bit different on the edges because of this distance here is going to be the same. And so you can see from this type of mesh, and if we look at the field for that again, we'll look at the J field because that gives you the nicest contrast. But you can see it gives you a very nice solution on the surface, very smooth, and so on. For any current type of applications, actually the uniform layers is not necessarily the best. We can also use a case where we're looking at a logarithmic distribution of layers, and I have a solution here that I can show you. And if we look now at the mesh layering for that, we'll look at the solution mesh. You can see that the mesh is actually graded. It's much finer here, and the distance between the elements gets larger as it goes inside. And if we look at the same field distribution as we did before here, again, we can see that we can still view a very nice distribution. that we can believe in. Okay, so this is one of the aspects of the model that we're looking at. So let's go back to our transformer model. And I'm going to, this is a full model. As you can see, we have the full core. But I'm going to bring up a model which has okay, here we go, which is where we have used symmetry. As you can see, we've actually put in our surface impedance boundary condition on various components here. For one thing, we put it on the tank wall. We're gonna, let's just make this, turn these off here. So we can get a better feel for what we have here. Let me just, let's turn off the surface impedance here. All right, and we'll just turn the visibility of that off too. So now we can get a better view of what's happening. So we used surface impedance on various parts. I also did it on the, put it onto the structural parts here, not just on the tank. So let me just turn those back on again so you can see that they're actually also applied to that. In this case, the steel shunts are non-conducting, although possibly conducting for this problem. We'll just look at what the solution looks like for this particular application. So let's go back to our field, and we'll look at our current density and have a look at what happens on the various parts of the model. Okay, let's turn off some of these parts here from the view so we can better see what's happening. So you can see how the field has been distributed on the structural parts with less current density on in the center and more along the edges of the structural parts. We can also, let me just bring back the back wall here. So, oops, that's not the one. There we go. And you can see how what happens here with the shunts and the distribution in the back. Let me just get rid of those shunts so that we get a better view of what's in the background. And you can see how the shunts are actually shielding the tank wall. This particular example, this is the use of the shunts demonstrates how you're reducing the losses in the tank wall. Of course, the tank wall being cooler, you run into fewer problems with the and so on, so that you can deal with these problems using a shunt. All right. So let's have a look at the ohmic losses in this problem. As you can see, we report all the losses in the various parts, including the coils. These are the coils, the covers. So that's the tank wall and the frame, and the core itself has some iron losses associated with it. So, okay, in this case, we have a material that doesn't have an iron loss. Let's just bring up one that does. So this is basically this is going to be basically the same Same model, but with a slightly different material. So let's go back to the results here and have a look at the iron loss. And as you can see now, the core body has the losses split up into the hysteresis component and its time average eddy current component. And we also have the same thing for the shunts, because the shunts are also have a loss associated with it. But in this case, we can't identify the eddy current portion because of we only have a single frequency to this model, to this material model. And the last thing I want to do before going to questions is I want to show you some of the circuit capability that is built into MagNet. And of course, circuits can be used for many reasons. In this particular case, we'll be looking at the circuit for, and we'll be adding an output circuit to this model. And so let me just bring up a window showing the circuit. And as you can see, we can create a circuit and leave other parts out of the circuit. If you look at the coils here, they actually already have their current-driven coils. We have the number of turns. We have the current in each of the coils in its phase. But for the output side, we've just connected it up to a series of resistors. This doesn't have to be resistors. There's going to be various other types of, it could be capacitors and inductors as well, and so on. And these will be applied to our nonlinear AC solution. It doesn't have to be a transient, and this is unique to MagNet, that you can actually solve for the fields in with using a circuit with the AC analysis solver. And if we look at our results, we can see things such as voltages across the various coil and circuit components. So here we have the resistors and so on. The current as well. This can be displayed as magnitude and phase, but it can also be displayed as real, imaginary, and so on. Iron loss can also be calculated. And so it's calculating that now. What takes time here is the actual time averaging of the solution. And of course, we'll also be able to see the ohmic losses in the surface impedance model components. And there we have, again, the core in this case, I didn't have a loss curve for that particular material, so we don't have a hysteresis value, core loss value, but we have the core loss values for the shunts, which again were modeled, totally modeled. They weren't actually modeled with the surface impedance. And of course, again, looking at the values for the various conducting bodies, we can get the ohmic losses for those. And of course, all these quantities can be selected and cut and pasted into a spreadsheet, for example, or a Word document, perhaps, for further diffusion to other people.